He also has a master's degree in astronomy and astrophysics from KU Leuven, Belgium. Nagraj has actually mentored a lot of students over the last few months and has also been a speaker in several workshops that Nakshatra has conducted, mostly in the domain of observational astrophysics. So if you're here today and you wish to do something related to the domain of observational astronomy or astrophysics, then he's definitely the person to listen to, but also ask all your questions to. As usual, please keep your microphones muted unless you have something important to say during the Q&A session. And also put all your questions in the chat box. So we'll get the evening started, and thank you, Nagraj, for your time. And all the rest of you, hope you find this useful. Please engage in the discussion. We will give the last 15 minutes time for everyone, and feel free to unmute during that time. Thank you.
Yes. So I think we'll start now. Yeah. Initially, first of all, sorry for being late. My computer just decided to update at the last moment. Okay. So let's just start with the essential techniques in spectroscopy. The way this presentation will go is initially I will do some boring stuff, which is introducing what spectroscopy is, how do you get a spectra, and all of those very trivial things. A lot of you may already be familiar with it, but there is always a necessity to set the base and then go into the individual technique part. The last part of this talk, which is the second part of this talk, will be much more practical oriented, where I will show you a few things that spectroscopy is used for, and then also the current research that is going on that I am currently working in also. So that's how it'll be placed across. To start with, I hope everyone knows, everyone can see a constellation here, and a lot of them should be familiar with what constellation this is. This is the Orion constellation with the Orion Nebula you can see it here. This will be useful at some stage of this presentation, so just keep that in mind. Starting with what is astronomical spectroscopy, or what is stellar spectroscopy. Spectroscopy is a study of spectra, or like you take the light from the object and then you split the light into its constituent colors, and then you study this constituent colors individually, and that is called as spectroscopy. In astronomical spectroscopy, you take spectra from a light source, which is usually stars, galaxies, other kind of interstellar medium, etc. And they have a particular spectrum of their own. There are a few different types of spectra. The most basic one is the continuous spectra, where you can see that it is the waveguide that you see, a rainbow that you see, basically going from one end of the optical to the other end. You can also continue this with other wavelengths, but in this talk, I will primarily concentrate on the optical or the visual wavelengths of light. So this is an example of a continuous spectra. Whereas in astronomy or astrophysics, what you will deal with is something called as a stellar spectra, or spectrum which is not continuous but has a lot of absorption lines in them. You can see the comparison between the two, the top one and the bottom one. You can see a lot of lines around, and these are three different spectra, and all three of them have a lot of lines in the blue region, in the green, as well as in the red region. These are the typical type of spectra that you will deal with in astronomy. Does someone have an idea of, you can see that this is the strongest line in the spectrum. Does someone have any idea of which line this could be? If yes, you could maybe unmute yourself and just tell what it is. The one in the red.
Maybe the H for beta.
You're very close. It is H alpha. So it's
H
around,
alpha.
because H alpha is one of the strongest lines in a spectrum. It's around 6,500-ish a region. And yeah, so there's also a few other lines, the H beta and H gamma. Those are all very strong lines. But yeah, these are generally the typical wavelengths that you will deal with. So yeah, why do spectral lines appear? So spectral lines are a very unique characteristics that allow us to study stars and galaxies, etc. Why do they appear? That is a very interesting question to understand the formation of the spectral lines so that you can later study them. So when you take a light source and then you pass the light source through a gas. Initially, when you look at just the light source or a black body, something like a black body, that is when you get a continuous spectra. So there is just the light continuously in all wavelengths. But when you pass it through a cloud of gas or a cloud of molecules, which is made up of different elements like hydrogen, helium, which are most abundant in the universe, what happens is the electrons in these atoms, they absorb energy, and then this creates the significant spectral lines. Higher the wavelength of spectral line, higher is the energy absorbed by the electron. So they jump from one shell to the other, which you would have studied in your basic physics class. So that is basically how you get an absorption spectrum. There's also something called as emission spectrum. You get emission spectrum when you look indirectly into a heated gas. So there is no light source behind the gas, but imagine that that a gas is heated. What happens is it emits in all directions, and then if you observe with one particular angle, you find only the lines which were absorbed by the cloud and then re-emitted across. So as I mentioned that the stellar lines are caused because of absorption from certain elements. You can see that there are many different type of elements spread across the region. This is not even the whole list. This is like only the most prominent lines uh, present across the region. There are hundreds and hundreds of thousands of lines in a stellar spectrum. If you take like a sun spectrum, there are like thousands of lines. There is something called as line list. So a lot of institutions have created these line lists where they give each line associated with what element it is. And there are thousands of entries in it, which is just insane to imagine. Next, we'll come to how our spectrum is observed. So how do we get a spectra? The instrument that we use to get spectra or spectrum is called a spectrograph. And these are one of the most commonly found instruments across. So if you look at a telescope, there are usually two types of instruments mounted on the telescope. One is a photometry, which monitors the brightness of the stars, and second is a spectrograph. Spectrograph is basically to get the spectra of the objects. Among the spectrographs, there are a few different types. One is a single slit spectrograph, and this is a simple diagram of a single slit. So what happens is in the spectrograph itself, there's a small slit. So you can see the slit here, through which a small amount of light is allowed, and then there is some kind of collimation, and then it is sent through a Eshel grating or a diffraction grating where the light is split into multitude colors, and then there are photo detectors which detect each region of light, and then you can reconstruct a spectrum. This is a very simple form. This is also a very common form because it's simple to make. It's not very expensive, and they have been doing this from quite some time. So it's very commonly found across a lot of different telescopes around the world. The most promising and upcoming spectrographs are called MOS or multi-object spectrographs, where there are in one spectrograph there are multiple slits, there are multiple fibers, so you can obtain a lot of spectra together. So instead of observing one star at a time, you can observe like 1,000 stars at a time and get spectra of 1,000 stars in just one go, which is insanely efficient. Then there is something called as IFUs or integrated field units. So this is usually very helpful when you're dealing with very large celestial bodies. Like if you take Andromeda, for example, if you want to take uh, spectra of Andromeda or some other close galaxies, it is not possible to have the whole object in one fiber because the object is so large. Instead, what you do is you cut the objects into multiple pieces and then you observe each in a different time and then or with a different fiber, and then you fuse it together to form a single spectrum. The few examples of very prominent spectrographs around the world are US and HARPS. US and HARPS are high resolution spectra, very high resolution. So they are one of the highest resolution spectra. By resolution, I mean the ability of a spectrograph to differentiate between two wavelengths. So higher the resolution, much better is the wavelength detection of very weak lines. And US and HARPS are the European Southern Observatory instruments, which are mounted on the Very Large Telescope in Chile. Weave and Muse are the two upcoming, two new instruments which have this MOS kind of spectrographs, and they can observe a lot of stars together. Whereas NIRSPEC is a near infrared spectrograph which is mounted on the JWST. And is one of the most complicated spectrograph that was designed because of a lot of other constraints which comes with a space mission. So this is a cross section. This is just a cross section of how light works within the NIRSPEC. And you can see the amount of reflection, the amount of complexity of the instrument is just insanely high. The second, so there are two things very important in us when you talk about a spectrograph or a spectrum. One is the resolution, one is the wavelength coverage. As I mentioned, resolution is just the ability of the telescope to kind of detect two very close lines. So imagine if there are two very close lines. Something like US, which has the highest resolution in the world, can easily tell you that there are two lines there. But if you take a very low resolution spectra, then the two lines will just appear to be one. You will not be able to differentiate between the two. And therefore, sometimes it's better to have a high resolution spectra also. Wavelength coverage is basically how long of the wavelength can it observe. Like something like Weave and Muse can observe the whole optical region, that is from 380 nanometers to 670 nanometers. So from violet to red. But there are few instruments that only can observe like 300 to 400 nanometers of wavelength. So very specific regions of the visible light, but not the whole length of the visible light. So those are also important constraints to have. The data that comes out of spectrographs are not the 1D charts, the 1D spectrum that you look where the lines are very clear. You can see just a line graph kind of a thing. But this is what you get. The image here is exactly what you get from a spectrograph. This is because the spectra that the spectrograph is taking is actually a 2D array of different orders and different wavelengths. So each line here corresponds to certain wavelength region, and then you need to add all of this together to get a actual spectrum that you very well know and have seen. And this is called reduction of a spectrum. Coming to the stellar classification part, again, a lot of you will know this, but still I will go through it just to have like an entire, you go all through the basics to the complex part. Stellar classifications, stars are classified into a few different types, mainly based on their surface temperatures, which is also analogous with the size of the stars. Not all the time, just the main sequence itself. They are differentiated into O, B, A, F, G, K, M, and the names are due to certain historical reasons. O stars are the hottest stars with temperatures more than 40,000 Kelvin. So very, very hot stars. And these are also very massive stars with masses in the range of 30 solar masses, 40, 50 solar masses. So 50 times the mass of the sun, etc. So quite massive stars. Next comes the B stars with temperature ranges between 20,000 and I think 30,000 Kelvin. And these are also quite hot and quite massive. And then comes A, F, G, K with decreasing temperature, with the M type stars being the coolest type. Um, we also assign a subclassification and a luminosity classification. So you can see that between O and B type, there is such a large temperature range, right? So B type is about 20,000, O type is about 40,000 Kelvin. There is a 20,000 Kelvin difference. How do you differentiate between these also? And therefore you give numbers like B1, B2, B3, O0, O9, O2, O3, O9, and those kind of things. So O0 is the hottest star. O9 will be very close to B. So O0, O1, O2, O3 goes on in the cooling order. And then as you reach O9 type, you then jump into B0 and then B1, B2, B3, B4, etc. So these are the subclasses. And then there is also luminosity class. The necessity of luminosity class is to differentiate between the main sequence stars and the evolved stars. Because usually when stars evolve from main sequence to red giant branch, they become very luminous because their radius increases, but their surface temperature actually decreases. So if you don't really take the luminosity into consideration, you might think the star is like, you can think that an A star is the G star because the temperature is decreased because of the increase in radii, but that is not the case. So that's why luminosity classes are given, which are depicted with a Roman numeral. Our sun, for example, is a G25 star. G is the type of classification, with 2 being the subtype. And then this Roman numeral 5 representing the luminosity classification of a main sequence star. So our sun is a main sequence star. That's why it's a G25. Another effect of this type of classifications is, because we are classifying it based on the temperatures of the star, the type of elements found and type of ions found in the stars also changes with temperature. Something like ionized helium, which is, so you know that helium is a very stable compound. So ionizing something very stable is extreme. It takes an extremely large amount of energy. And therefore only the hottest of the stars will have a lot of ionized helium. You can see how fast it drops as you decrease the temperature. And then something like neutral helium will the effect of neutral helium will be highest for around B stars. So these kind of things can also kind of give you an idea of what type of stars you're dealing with. If you look at a spectrum and you find a lot of neutral helium but very little ionized helium, you already know that it's a B-type star with temperatures very close to 10 to 30,000 Kelvin. So these are very crucial information that you can obtain by just looking at a spectrum, not even like doing analysis. So for just comparison between different spectra, these are individual spectra for different types of different classifications of stars. You can see that O-type stars, B-type, and A-type. You can see that some spectral lines are much stronger in A-type stars, whereas they are almost non-existent in a K-type. These are the differences that you look for when you look at a spectra to kind of distinguish which type of stars you're dealing with. And then the M type, which are the coolest types, you can see the spectra just goes crazy because these stars are cool enough to have molecules in them, something like titanium trioxide, and molecules kind of result in a very different looking spectral lines compared to, like, single atoms, and therefore their spectra is completely different when you compare to like an A type star. Coming to the second part of the presentation, where we talk about how spectroscopy can be used and what different stuff can be done with it, the use of it. There are a few uses that I've written here. There could be more, but maybe we'll not have time to go through all of them, go through all of those others. I will go through these importantly because these are the basics of spectroscopy. first thing that you can analyze from the spectra is stellar temperatures, which is a key ingredient to kind of do further analysis. Then you can understand the rotational velocities of the stars by just looking at a spectra. Rotational velocity meaning how fast the star is spinning around its rotational axis. The third one is radial velocity. Radial velocity is how fast the star is moving away or towards you. So with you as the in the line of sight. This gives idea. I will discuss in detail a little bit. The fourth one is the chemical compositions of the stars. So you can analyze the spectral lines to obtain the abundances of different elements present in the star. You can also understand a lot of evolutionary mechanisms by studying chemical compositions. The fifth one, which I might not go into because this is slightly more advanced, is stellar interiors. You can look at stellar spectra and actually understand the interiors of the star, which is one of the most complex things out there, because when you look at a star, you only look the outside, the photosphere, but you cannot really look into the star. But there are certain techniques which allow us to do this. Coming to the galactic spectra, where you take spectrum of a galaxy, there are you can learn something with the motion of galaxy, that is redshift or blue shift, and you can also learn the interstellar medium. So there is something called as absorption, the Lyman forest, which happens because of the high redshifting and interstellar medium. This gives you idea about what type of elements are present in interstellar medium and then how it affects the overall environment. Let's go one by one with not too much into detail, but just grazing past a lot of it. Coming to so first one is temperature estimations. I think I mentioned that the classes were classified based on the temperature itself. So already you can see that different spectra of different temperatures are different from each other. They're not the same. But one thing that you see across all the spectrum is the peak of the spectrum is different. It goes through lower wavelengths as you go from hotter stars to cooler stars. This is basically the representation of the black body, the Wien's displacement law, if anyone remembers. So by just measuring the peak of the flux, the peak flux of the spectrum, you can already use Wien's displacement law to understand the temperature of the star. This might not be extremely accurate because of certain phenomena that are inherent to the instrument, because not all spectra will look this clean. Instead, they will have instrumental noise that creates certain disturbances. So it will be hard for you to measure the max, the lambda max. But in case you have a good spectrum, then you can just measure the peak flux, the peak wavelength, and then use this equation to find the temperature. The another way of identifying temperature, again, it all depends on this black body distributions, is by just the color of it. So as I said that hotter stars emit more in the lower wavelength, whereas cooler stars emit more in the higher wavelength. If the temperatures are quite correct, then you see that the hotter stars, which are the O-type stars, they appear to be very blue in color, whereas cooler stars appear red or yellow in color. And you can go out in today and look at the sky, though city skies that you might be in are not very good at, to look at. But you can just look through, and if you see a blue type star, then it's most probably a hot star. And this is the Orion constellation that I was talking about. This is a very good representation of a hot and a cool star. So you can see that a lot of these Orion constellation stars are quite blue in color, which are most likely to be quite hot in temperature. But there is one particular star here, which is you might know it as the Betelgeuse. So Betelgeuse appears quite yellowish red in color because this is actually a red giant star, which is quite evolved. and might go supernova in very soon. If you have seen the news or looked at research papers, you know that there is a paper that says this might go supernova in next few decades. So very soon. Yeah, so this is a very cool star because it has the radius of the star has increased so much that the temperature has fallen. But yeah, you can just look at the color of the star and kind of make a guess of its temperature. Coming to rotational velocities. So rotational velocity, let's look at this spectrum. There are two spectra here, the blue one and the red one. And if if you look at them carefully, you can already know that the red one has broader lines. You can see that the blue one is much thinner and much deeper, the spectral lines I'm talking about. And the red ones are the shallower spectral lines, but quite wide in the quite wide spectral lines. And this is a representation of the average. You can see that the blue one is narrow and deep, whereas the red ones is quite broad. What is the cause of this? The cause of this, is something called Doppler effect. I think everyone will have heard about this. Doppler effect is basically shifting in wavelength of light based on the velocity of the source where the photon is emitted from. This broadening of spectral lines is caused by two different phenomena. One is rotational broadening and one is thermal broadening. Both are Doppler effects, but there is quite some difference between the two. With rotational broadening usually being much more significant than thermal broadening, but you should still understand that there are two different phenomena that lead to this and not just one. Rotational broadening is when a star is rotating. I don't know if I have no. When a star rotates through when you look at a star that is rotating quite fast, then the star will actually have two halves of the star. One half of the star is coming towards you. So because it's rotating like this, one half of the star is coming towards you, whereas the other half of the star is going away from you. The one coming towards you will be shifted in the opposite direction to that of the one going away from you, and this creates a gradient in velocities. And when you calculate Doppler shift in each of this gradient, you see that the value is different, and that leads to broadening of the spectral line. And all this is also the reason why with higher rotational velocities, you have much larger broadening. So if you think like the first spectra is like 10 kilometer per second, the rotational speed, the second spectra will be like maybe 60 to 80 kilometers per second. But if you go to stars with 200 kilometer per second, the lines will be they will not be pointy. They'll just be like very smooth lines because they have broadened so much that they're very shallow in depth. Why is rotational velocity important? You might ask, like, why is this even important to understand how stars are revolving? There are three very important understandings that we get from this. First one is a mass transfer signature. Generally speaking, stars, if you look at a distribution of a lot of stars, you will find some stars with a very high rotational. So I'm talking about when they are born. So when they are born, some stars will have high rotational velocities, some stars will have low rotational velocities. So there's not a particular distribution that's going on that biases to one side. But we know that as stars evolve in the main sequence itself, there is something called as magnetic braking that takes place. Basically, the magnetic field of the star slows down the star. So we generally expect stars to slow down as they evolve, and this leads to very slow rotational velocities in the stars. For example, our sun, which is a slightly evolved star, has a rotational velocity of just 2 to 3 kilometers per second, which is quite low in the sense of, comparative to some other stars. But we also see quite a good population of stars with rotation velocities of 100 kilometers per second, 200 kilometers per second. These, one of the mechanisms that such high rotation velocity stars are created is something called as mass transfer. They basically have a companion. So there are two stars in a binary system that revolve around each other. Then one star becomes bigger. There is some mechanism called Roche-Loeb overflow. That happens where the companion is giving mass to the other star. So you can see here that this large companion is giving its mass away to the smaller star here. So when with the mass, not just the matter, matter is obviously transferred from one star to the other star, but another significant thing that is transferred is angular momentum. So the star that gives out the mass is actually losing angular momentum, whereas the other star is gaining angular momentum. And this kind of spins up the star. So it increases the rotation velocity. So when we look at a star and it has a very high rotation velocity and we don't see any other phenomenon going on, then it's a clear signature that mass transfer has happened. There is some interaction with the binary it has. And this is a very important thing to when you're particularly studying some very peculiar stars, to have this information that, oh, it had some interactions before. Then there is something called as rotation induced mixing. This again is a complicated phenomenon to kind of go deep into, but you know that stars, a lot of stars, almost all of the stars have two different type of heat transfer. There is convection zone and there is radiation zone, radiative layer or convective layer. Convective layer is basically just like your water boiling. So a lot of mass, a lot of, a blob of the plasma goes up and down, up and down. So there is mixing going on. This mixing is actually enhanced by rotation. So faster the star rotates, more is the mixing. Why is this mixing important? Because when a star is using all the hydrogen present in the core, while it's evolving, it's fusing hydrogen into helium. At one point, it's done with all the hydrogen it has. So it no more has any hydrogen left in the core. So it cannot fuse anything. So it starts evolving into the red giant branch and etc. And all this evolution goes on. But if mixing is increased, the star keeps getting new source of hydrogen because hydrogen is brought from the outer layers into the core. So it extends the age of the star, where it can fuse more and more hydrogen into helium and live longer. So that is the important aspect of why rotational velocity is important. Rotational velocity is useful to study. The third one is synchronization, again dealing with binaries where if the two stars are too close, then something called as tidal effects happen. It's basically like gravitational forces of each of the stars affecting each other, and then they kind of synchronize where the rotations of both stars are equal to each other. This phenomenon is also happening with the Earth and the Moon system, where Moon is actually influencing tidal effects on Earth, and it's actually slowing down the rotation of Earth. So our days, the length of our days are increasing every year because of this phenomenon. Though it is not noticeable, it's very negligible, it's still happening. Coming to radial velocities, which are one of the most important concepts in current day astronomy because they give a lot of information. You know that the basic information that radial velocities give is redshift and blue shift. It tells you if a star is moving away or if a star is coming close. The same phenomenon, which is also Doppler effect, can be used in case of a binary. So here is a representation of a binary. There are two stars represented by A and B. A is the yellow star, B is the red star. They are going across a circle, which is a hyper simplistic way of representing a binary. You can see that at one position, let's wait for it to come back. Yes, at this position, the velocities of the two stars are tangential to our line of sight. So this is the line of sight. When they are tangential, there is no Doppler shift happening. because the stars are not moving away or towards you. They are just moving across the plane, which does not influence any Doppler shift. So you will see just single lines. Even though there are two stars, you will just see single lines because the wavelength at which this transition happens is the same irrespective of which star you're looking at. So H alpha will always be at 6,500 and something. I'm not exactly sure of the wavelength, but yeah, it will always happen at that exact wavelength. But when the stars are moving towards and away from you at this particular, you can see that A star is moving towards you, B star is moving away from you. Then the line of A star will be shifted much in opposite directions to the B star. So you can see that the one line actually splits into two. So A is blue shifted, B is red shifted. And you can see that the B line has higher wavelength compared to the original single line. So it is red shifted, whereas, sorry, B, whereas A, which is blue shifted, has a lower wavelength. But when the stars come back again to a tangent, so as they go around the orbit, they come back to a tangential zone. These two lines again fuse to one, creating only a single line. So there is no Doppler shift. And then again, when they go around, they create another two lines. This type of systems where lines are kind of becoming 1, 2, 1, 2, 1, 2 are called as spectroscopic binaries. And in this particular case, it's called SB2 binary, so spectroscopic binary 2, because there are two lines moving across the spectrum. This is useful because it helps us identify the systems and also measure the radial velocity. This is a hypothetical kind of, a very simplistic diagram, a representative diagram. And now I'm showing you a real spectrum. So each of these lines, each of these colored lines is actually a spectrum, but it's the wavelength is quite short. It's between 4,650 angstroms to 4,720 angstroms, so about 70, 80 angstroms of length. This is just to zoom into this one particular line. This is the helium-2 line because the stars are quite hot. Here you can see that the spectral line is a single profile. You can see there's just one profile. But as you go to the next spectrum, you see the spectral line profile changing. It was quite pointy here, but it's kind of smoothened out. And in the next one, you can see that there are two lines appearing. There is one line here, and then there is another line here. This is because these spectra are taken at different times. So you observe the same system, you obtain a spectra at different instances, and this kind of technique is called a multi-epoch spectroscopy. And you can see that the two lines again merge back to one. So we go back to the single profile again. So this kind of gives you a real idea of, oh, there is some motion in the system. There is some movement going on, which is blue shifting and red shifting the lines. You can measure them. You can do something called as a Gaussian fitting, where you take two Gaussians, one for each individual stars, and then you fit them. So if you take this one, which is where there are quite well separated, you can fit two Gaussians. You can see that this is the spectral line from the primary star, whereas the smaller one is the spectral line from the secondary star. And then you can measure the center of this line, and then you can see how much it has shifted, and then you can use Doppler equations to calculate the velocities of the star. And here the same fitting is shown for a single profile star. You can see that even though the line looks like a single line profile, there is actually contributions from two different spectral lines. You can see the secondary here and the primary here. From this, you can get something called as a radial velocity curve, which kind of tells you the x-axis is time. So as time progresses, how does the velocity of each of the companions changes? Here you can see this is the exact system, the radial velocity of this system itself. So I have measured it for each individual spectrum, for each individual line, and I obtained this. Ignore the different colors, only look at the blue squares and the blue triangles. The other two colors are basically the same, but with different lines. So the blue squares represent one of the companion, which is the primary companion, which is the much larger companion. And the secondary companion is represented by the triangle, the blue triangle. You can see that as time progresses, the velocity, the radial velocity of the primary companion goes from about minus 40 kilometers per second. It goes all the way up to about plus 40 kilometers per second. Whereas the velocity of the secondary is going from minus 20, from plus 25 to minus 125. So you can clearly see this crisscrossing, and this is a good representation that your sampling is quite good. But it also shows that there is quite a big motion in the system itself. And by something called as phase folding this, which is where you take this and then you fold the curve on itself, because this is a very large timeline. This is a small timeline, but you can have a very large timeline, and then you fold it with the orbital period. When you fold it with the orbital period, the curve quite nicely appears. You can see here it's a orbital phase, so 0 to 1. You can see how nicely the stars are moving across with respect to each other. So they're moving with respect to each other, and that's why this crisscrossing happens it happens twice in one orbit. And you can model this system. So the points here are the one that I measured, the points here, and the dotted curve represents the best fit model. So it's a model that I fit to kind of get estimates about the masses of the star, not the individual masses, but a mass ratio, which tells me about how massive each of the stars is with respect to the other, and and also some details about the inclination of the system, etc. So this is quite a useful technique for studying things like eclipsing binaries and just binaries in general, which can then be substituted with some other techniques to go ahead and have a deeper analysis of the whole thing. Other uses of radial velocities include galactic rotation. So if you study the stars, so take Andromeda, for example, if you study the velocities of the stars in Andromeda, the redshift and blue shifting of Andromeda at one direction, you can understand how fast the galaxy is rotating. And this is one of the methods you can measure the differential rotations in galaxies. Identifying the motions of galaxies, again, blue shifting and red shifting, these are unresolved galaxies. So you take galaxies from very far away, very high redshifts, and you can measure the redshift and blue shift of those galaxies, which can then give you some evidence about the accelerated expansion, because galaxies farther away will be moving away much in a much more rapid way compared to the galaxies near you. Coming to chemical composition, again, I mentioned absorption lines are made from different elements. So in theory, you can measure these lines and you can get information about how much something is there in the star, like how much oxygen is there in the sun, how much sodium is there in the sun. You might not even know that sodium is there in the sun, but there are trace amounts of a lot of elements. There are also heavy elements, not just light elements. There are also heavy elements like yttrium, europium, um, lanthanum, which is quite a heavy element. So all of these elements are present in a lot of stars, and you can measure them using the spectral lines. There are two particular ways of measuring the equivalent, the abundances, which are called equivalent width and spectral synthesis. Equivalent width is basically you look at the line, you measure the equivalent width. I think everyone should know what equivalent width is. It tells you about the area encompassed within the spectral line, and you can use theoretical models to kind of equate that with abundances. Spectral synthesis is a very special one where you actually create an artificial theoretical spectrum and then you compare that with the original one. For example, like you can, this is quite I can show you how spectral synthesis work. This is actually spectral synthesis, one of the most recent, not most recent, but it's quite an important way of doing it. So what I do is, so here what I'm doing is, I have a spectrum of a star and I'm trying to identify the oxygen composition in the star. So I'm trying to analyze how much oxygen is there in the star. The way I do this is let's wait for it to model this. Yes. So the way I identify is there are a lot of, so I know that this particular line at 6,300 is an oxygen line. So how do I know this? There are catalogs of spectral lines that give you this information about which line is different elements. So I know this is an oxygen line. What I'm doing is ignore the first one. First one, the blue line, ignore it. It has very minimal oxygen in it. So you can see here, I am inputting three abundances. I'm putting abundances of carbon, nitrogen, and oxygen. Carbon and nitrogen stay same in all four of them. But oxygen abundances, what I'm doing is I'm synthesizing an artificial spectrum with different oxygen abundance. You can see that oxygen abundance is increasing with the color. So as I increase the oxygen abundance, you can see that the line depth increases. That is quite intuitive. More of some element, then more deeper the line because more the absorption. And then I'm comparing that with the observed spectrum. So the white line here is the observed spectrum that we obtained from a telescope looking at the star. Here you can see that the yellow line, which corresponds to this much oxygen, is not a good representation, nor is the red line. It's an overabundance. It's not good comparable. But the green one, which with an oxygen of 8.49, this is close. It is not exactly the same, but close approximation to what we find in the observed itself. So by fine tuning this, I can actually obtain oxygen abundance quite, this is how easy it is to obtain it. You redo this kind of analysis for all the elements present, or like whichever you're interested in. There are about 25 to 30 elements that you might be interested in, and you can kind of analyze all of them and get an thing about how much elements are there. And these are showing you the nitrogen abundance and the carbon abundance, how they are derived, etc. Why is this important? Obviously, stellar abundances are important to understand how stars evolve with time and also how nucleosynthesis happens. So how are different elements produced across the universe? You can understand this, something called as galactic archaeology. And we also understand the evolution of the universe because as time progresses, the amount of hydrogen is reducing, whereas the amount of something like iron is increasing with time. So because stars are fusing hydrogen into heavier elements. These are some of the very useful current research going on. So whatever you see here is actually my current research that I'm doing in PhD with stellar synthesis, with spectral synthesis, and understanding the chemical evolutions of certain clusters, so globular clusters and open clusters. So I will stop it there for now. I will not be going into the stellar interiors, which basically is astroseismology, because it's quite complex and I'm not sure if that is even useful at this stage. Thank you. So I'll be taking any questions if anyone has it. I don't think there's any questions.
Hey, Nagraj, have you been going through the chat box on the Zoom call?
Oh, no.
There were, I mean, I guess you can just go through them. There were quite a few messages as you were talking. And maybe some can be addressed. But yes, if anybody else has questions, please feel free to unmute now.
Oh, that's quite a bit. Hello, nice to meet you again. Yes, what Kshitij says is quite accurate because what I showed you is only the optical part, but there are spectral lines almost everywhere in the spectrum. You can analyze them to understand different phenomenons. And so each wavelength probes a different region of, different kind of temperature regions, and you can understand them to have a lot of additional information. But the talk that I gave you today is only restricted to visible because that is what I work with. But if you have heard of JWST, it's doing a lot of research in the infrared region where there are also lines, a lot of spectral lines. And actually, if you look at this graph here, if you look at the graph here, this is actually the infrared region, and you can see a lot of CN lines, so carbon nitrogen lines across, and even this is an infrared region. So there are lines across the wavelength spectrum.
Hello, hi, Nagaraj.
Yes.
Okay, I'm Asmi. So actually, I'm interested with this chemical composition things. I just want to ask you regarding the spectral that you did.
Sorry, I can't
hello?
hear you. It's very
Okay.
yeah. Yes.
My voice clear?
Yes.
So are you producing the abundance using the stellar evolution code?
This one.
Yeah.
So here we use something called as a radiative transfer code. So what we do is we have to give things like the temperatures of the star that we want to analyze, the log Gs, the metallicity, etc. And then we also need to give model atmospheres, which are basic cruise model atmospheres. What the code does is it takes all of this and then it calculates the line strength at each individual lines. So this is usually done through radiative transfer codes. No, still not stellar evolution codes because they do something else. Here we are using codes like Moog, if someone has heard about it, or TurboSpec. That these are the most used, highly used radiative transfer codes available.
I see. So it is different with the stellar evolution code, like MESA or something.
Yeah. Mesa also gives you information about abundances. Like if you go to Mesa, it does give you a lot of information about how the abundances change over time. But what Mesa is built for is evolving stars from, evolving through the stars throughout their lifetime, right? Mesa is basically constructed for that. Here, we are not really interested in that part. We are only interested in current chemical abundance of the star.
I see.
You can combine this with Mesa to obtain additional constraints. But yeah, I am not doing that for now.
So the difference with the MESA code is that it is just focus on the current profile of the star, not throughout the lifetime of the star.
Sorry?
So means that the code that you are using to produce, okay, this result is different because it is only focused on the current profile of the star, not throughout the lifetime of the star.
No. So we can only measure the spectrum that we have. And the spectrum that we have is current spectrum. We can't get a spectrum of like 1,000,000-year-old stars, right? So that's the thing about abundances. So we can only measure it right now. The way we do galactic archaeology is we look at star clusters because we know the ages of the clusters quite well. So we can look at older clusters, we can look at intermediate age clusters, we can look at new clusters and see how chemicals have evolved over time. So that is how one way we deal with different ages of stars.
I see. Okay, thanks.
Thank you.
Hello, Nagra.
Hello.
Yes.
My warm greetings to all. I am Nagesh Vatnala. So,
hello.
My question is, you said that reduction of spectra, it's a basic one. So how can we do it? What are the special skills required, technical skills required?
For reduction?
Yeah, reduction of the spectra. See, we get raw images or flats from
to be honest,
pipeline.
To be honest, I've never done reduction myself.
Oh, okay.
Okay. The thing is, yeah, this is the most talked about point in talked about thing in astronomy, because a lot of new instruments have a pipeline built in which reduces the spectra automatically. But there's like a long debate that the new current age of students don't know how to reduce the spectra, which is quite true. But a
Yes.
reduction in spectra, the general case of what you do in reduction of spectra is, initially you start with something like corrections, like flat field corrections, bias corrections, and all that, which
Okay.
is simple because when a telescope is observing, it's not only observing your star. It would have done something called as a calibration run. So in calibrations, it has particular standard standard spectrums. They usually use some kind of light, like neon lights or something. I think tungsten neon light, where you know the spectral lines exactly, and they take that. You can use those kind of those additional data to kind of correct the spectrum for like flat field corrections, bias corrections, etc., which is then followed by wavelength. So here you can see that there is no wavelength. There is no wavelength. Where is the
Okay.
wavelength? You have no idea.
Yeah.
So you do something, you correlate your spectrum with another standard spectrum, and then you kind of give them the wavelength calibration. Because if your wavelength calibration is wrong, then everything will be wrong. Wavelength calibration is the at most important part of spectral reduction. But
Okay.
I am not a good person to ask this to, because I have never done it myself.
Okay. Is there, I'm just, I just wanted to know that is there any tools that we have to learn? See, image reduction analysis facility is there for image reduction. Like that, is there anything that I can do with tools, advanced tools like that,
Okay.
to do reduction of spectra?
So there are, so the go-to tool for at least the visible, the optical spectrums, the go-to
Okay.
tool for reducing optical spectrum from across the instruments is IRF. Have you heard of it?
Okay. Yeah. Thank you.
Yes.
Thank you so much.
IRF is a very old tool that was created years ago. But still, even after all these years have passed, there is no tool better than IRF for spectral reduction.
No. Okay.
And
Thank
people now even use the same thing.
you.
Yes.
Hi, sir.
Yeah. Just call me.
I'm a UG student, and I wanted to know which programming languages we should be familiar with to do computational analysis of spectrums.
Computational analysis.
Yes, sir.
Computational analysis, a lot of, so for just basic astronomy, you need Python. That's the only language you need if you're doing basic astronomy, like observational or something. But if you're doing computational, then a lot of codes are written in something called as Fortran. It's again a very old language, but for some reason, a lot of astrophysics softwares are written in Fortran. But you could also look into what are the new ones written? I can't remember any new softwares that have been written other than Fortran. It's usually Python and Fortran which are the most abundant. But Python is very bad for computational because it's so slow. So because Fortran is quite fast in terms of computational power, so it can do a lot of things quite quickly. I'm not really sure because I've never really looked into computational, because my stream is very observational astrophysics. But yeah, you should look into Fortran for now.
Okay, sir.
Hello, Nanda.
Yeah.
Good evening, everyone. I wanted to ask one thing, like when you're going for the graphs, helium or hydrogen, it is saying that 0.2 as a result
Sorry?
for the dotted sky blue line on the previous image.
This one?
Not this one, the previous one. not familiar with what the graph says. I wanted to ask only general question like what is the guarantee that whatever result you are getting is the accurate one, the real one out there? Or is there any tool to measure the accuracy of what you are measuring and what is there actually in the
I don't know if I understand the question exactly. You're basically asking how do we know what we see is the real thing?
Yes, yes. Like what we are measuring through softwares or readings is the like actual correct answer.
So you might be dealing with, you're telling about the spectral synthesis.
Yes, yes, correct. Yes,
Yes.
yes.
So
Yeah, here we can see 0 point of here second graph. 0.3, as you said, the first one is the hydrogen abundance. Correct? Am I correct?
So no. So what here is representing is so first graph is only representing the abundance of nitrogen. So the blue one is where nitrogen is completely absent. So -5 represents there is no nitrogen. So you can see that some lines are quite high. This tell me that these lines, you can see here, this is not a good, here I'll tell you here. So anything where the lines are not, for blue lines are like going straight, tells me that that's a line. Because if there is no nitrogen, there will be no CN line. And that's why the line strength is almost 0.
Yeah, understood that correctly.
Yeah.
Like I'm asking what is the guarantee, like what is the accuracy, what we are measuring is true.
So
is there any tool for that?
So what happens generally cases, these models are built over only after having years of observational data. Like, it's not like we first build the model and then we kind of, look at, maybe, and then we compare. What we do is we first have a lot of observational data. We kind of look at patterns in those observational data. We also have theory. So we have theory about how radiative transfer works in stars, how the lines are formed. We have a lot of theory across it. We can use that theory to construct a software that has a lot of, again, the theory is based on what we have observed before. It's not like out of nowhere we have this theory, right? But then we can construct a software around whatever theory we have, all the equations that we have. What the software does, the simplest thing the software does is solve those equations. That's all the software does generally. What we do is we then compare these two. If you're asking how do we know if this is correct, to test these softwares when they are made initially, they are compared to standard stars. And also these are compared to other techniques that are used. So abundances need not only be achieved like this. They can be achieved by a lot of different techniques. You compare these things with already known standard techniques, and then you see how well this goes on, how well this predicts something like, the abundances of like carbon, which is most abundant, one of the most abundant elements. And then you see if there is a match. If it matches, then you know that what you built is reliable enough. But if it does not match, then you know that there's a problem. The software that I'm using here, or any of the radiative transfer softwares, there are like 3 most prominent softwares. These softwares have been time tested again and again, because these softwares were built in early 1980s or something. I think around 1980s or 1990s. So it's been like 40 years of testing. So everyone has tested these codes again and again. And even to this day, they are still the best ones because they are so reliable in measuring the abundances. So that is the only way you can tell. Now, if you look at the newer trends, you see a lot of machine learning algorithms coming up. Like these kind of things you need not do anymore. There are a lot of machine learning algorithms that are coming up. Again, you might ask the same question. How do we know what results the machine learning algorithm is giving is correct? How do we know it? You can get spurious detections also. The only way that you can do is you keep testing the algorithm again and again. And how do you do that? You have a training set, and then you have a observed set. So you testing set. So what you do is in training set, you kind of train the algorithm the way you want it. and then you take real spectra from real stars, and then you and then you run this algorithm on those stars. And then you see if the values that you get from the algorithm and the traditional way is correct, is compare, they are agreeing with each other. And if they're agreeing, then you know that your machine learning algorithm is also as reliable as the traditional one. So this is generally how the models or the theoretical models kind of go ahead.
Okay, complete. Got it. Thank you. Thank you so much.
Yeah.
So, hello, it's Nagesh again. Hello. So, Nagaraj, since the brother asked about computational, I have a curiosity question. So, it's more like it's maybe away from the present topic. So, thing is, if there is a binary system, distance from our system, our observational systems or our space-based telescopes, like 100 light years away from us, if a binary star system is there. So whatever the spectrum we receiving is 100 years ago's light, whatever we are receiving.
Yes.
So is there any computational tools that we are working, I mean human civilization working, that we can further advancedly what do you say that further advancedly we can process the data we have, so that we can I'm not getting that word exactly.
So you're saying if there are anything that
we can foresee the 100 years of light, how it will be behave, the system will behave.
So we already have them. So these are called evolutionary codes.
Predicted. Thank you, Kamal.
MESA is a very good example of this evolutionary code. One of the more highly widely used software. So what you can do, if you have a binary, you can go to MESA, you can input all the binary details, and it will actually evolve your stars from pre-main sequence all the way till its white dwarf stage. So you can simulate you can simulate the system for billions of years, not even hundreds of years. You can simulate billions of years.
Entire life system.
Entire lifetime of the stars. Yes, you can do it. Is it reliable? Is it reliable? Yes, MESA is quite reliable. But is there a way that we can, if we simulate one star today, and then we simulate 1,000 years from now, how the star will look, right? How do you confirm it though? There is no way we can confirm it.
So it's completely ideal situations, whatever atmospheres are there.
It's not ideal. MESA has a lot of physics in it. It has a very realistic physics. But again, MESA is restricted to our current knowledge of what stars look like. And our current knowledge of stars is still not 100%. Because there are a lot of things in a star that we don't understand. We do understand a significant portion of it. So we understand enough to make an approximate, kind of prediction. But if you're asking if we can 100% predict what will happen, I don't think so. Because again, the universe is quite complex.
So is MESA predicts only for up to white dwarf itself, not for black holes or like that?
It can do black holes also, but again, we don't understand black holes. So it can tell you when the black hole is formed or when the supernova goes on. It can tell you a lot of details like that. But again, it's giving you those informations based on what is happening inside its interior, right? It's just modeling the things like fusion energy that's present, how much energy is going outwards, and how much gravity is interacting and all that. But yeah, it can tell you when a black hole is formed, but it cannot give you any information about the black hole.
Okay, it tells you when singularity happens. That's it.
It tells when the supernova happens. It tells you when supernova happens. But then after that, it's just unreliable because our physics is unreliable when black holes come into the picture.
Completely. Laws will change.
Yeah.
Okay, thank you for that. Thank you.
Hello. Hello,
Yeah.
Naman. It's Vishal again.
Yeah.
Hello. Like, I want to ask one previous question, like, how far we are, like, currently in the, from researching, as the researching is going on proving the parallel universe or parallel, whatever the existence, close to our existence. So how far did we get in that research? Or like, is there any form,
Sorry. Can
like,
you repeat yourself?
as the research is going on finding the proofs for the parallel universe
Yeah.
based on some assumptions, like as of we know, like dual state, or on that basis, some research is going on for proving of the parallel universe. Like, do you have any idea regarding that? How far did we get in that research, or any reference you can give me on
The thing is,
speculative
okay,
study?
let's start. So it might be a controversial take on something like this, but I believe the whole concept of things like parallel universe and multiverse has been blown out of proportion, because yes, there are theories that predict it, but there is no observational indications that such a thing exists. Yes, there are trying, so like something like CERN is trying to have detect. So CERN is trying to detect things like graviton, which could in theory tell us that there may be more than one universe, and gravitons can pass through multiple universes. But again, it's been so long, we have not seen anything, not even close. Forget 5 sigma detection. We have not even seen like a 0.1 sigma detection or something like that. So it, even though there is quite some research going on, I don't think we are anywhere close to even kind of start something concrete on it. We are quite, it is optimistic, I would say, but I don't think we are anywhere close. But given the fact that I am not really in connection with any of those things, because that is dealt by a complete different sub branch of astrophysics or like cosmology. I don't really have a lot of knowledge in that particular aspect, so I am not a good person to kind of answer this question.
Okay. Thank you,
But
Naman.
if it exists, I hope we'll find it one day. But I highly doubt it exists. So yeah.
Yeah, by my words, you might got to know that I'm really interested in cosmology. But I really managed to, every time I get managed to like really be bad at maths, especially differences and integration. But I'm really good at physics, science, and everything, cosmology.
Yeah.
So is that
Cosmology.
possible that I can move forward in cosmology? But
Yeah,
I do really hate maths every time.
it's possible to move forward in anything. Like it doesn't really matter. If you're interested, then you can do almost anything in physics. So if you're interested in that kind of a particular thing, you can definitely go through some of literature that's currently been written. You can look through, read through, see if it is interesting for you. You can also try to work on something. That is the best way to actually know if you like it. The best way to know if you like something is to actually work on it. By the end of it, if you're like, I don't want to touch it ever again, then you know your answer.
Yes, yeah,
So yeah, that's
100%.
a good way of doing it.
Is there any forum or websites for current research on cosmology or
Current
studies
research
or
on
masters
cosmology, all
related?
the papers, you should find all the papers in archive or ADS, which is Astronomical Database Service, I think, from Harvard. You can just go and type ADS NASA, and I think you should get to a portal where almost every paper, a lot of papers that are published day to day have been uploaded for free. So you don't even have to like pay for like journals. You can just go there and look through papers. You can also like, if you go to archive or astro ph as it's called, for cosmology it might be something else. You can go there and you can kind of you can enter yourself in a mailing list, and then it will send you a mail every day of all the papers that have been released that day in that particular aspect. So like I have Stellar Astrophysics has mailing list, and I get papers every day about what have been published in that particular field. So you can also try that.
Okay. Can you repeat that once again? The website name? Archive
Uh,
is
it's called Archive ARXIV, I think. ARXIV, yeah, Archive. And another is ADS NASA. Just go to Google and type ADS NASA and it should pop up. I can show you, I think. This is one archive. You can just search paper by your whatever you're interested in. And then the second one is this one. Yeah. So you can search anything. You can search like if I search stellar astrophysics, it'll give me all the papers from like 2023 to 1981. Nice, 1891, sorry. So it'll give you like shit ton of papers. If your search result is this general, then yeah, you will get a lot of results. But yeah, you can go, you can read through some papers that you like, see what interests you. This is how you find actually what interests you. And also the other way is working on a project, on a small project that you, if you can, and because that will give you a lot of insight also.
okay. Thank
Yeah.
you.
I think Yash has a questions in the chat. Sun contributions only 1% of angular momentum in the solar system. I'm not sure about the solar system, but the reason for slower rotation of the sun is magnetic braking. It's basically like the magnetic field of the sun is slowing down the sun itself. And this happens in every star. It's not just the sun, it's like everywhere.
That was actually that is not question actually. It is actually just the that means single. It is the just the statement based on your
Okay.
presenting.
Okay. Can you share the name of software you use for spectroscopy? Also, it will that if you share a paper that you work on. This any relevant papers. I can share so I work on a software called Moog. So this is, so I have put it here. It's called Moog, and it's a radiative transfer software. It's a very old software. Yeah, but this is also quite a very, it's quite a good software to work on. There's also some new softwares which do this quite which do this very iteratively, and you don't need to do so much input. And there is one software called PySME, which is Python version of spectroscopy made easy. That is the full form. Spectroscopy made easy PySME. So no, I don't write my own softwares. I'm not a to put it out, I'm not good at programming at all. The best I can do is write basic Python programs to do data analysis and to do plots. To do plots like this, I can do a good job. I'm not a computational astrophysics. In the thing that I do, you don't need a lot of coding. Can you predict magnetic strength of the star from spectroscopy? Magnetic strength of the stars from spectroscopy. I am thinking about this. In general, things like hyperfine splitting should make it possible for you to. So, magnetic strength kind of affects, I think it's called the Stark effect, which causes hyperfine splitting in spectral lines. But the thing is, this effect is so small that you need a hyper high resolution spectrograph to even have that resolution to, to kind of resolve such a small effect. I don't think we have any spectrograph that goes to that level, because the current highest spectrograph is UVIS, which has a resolution of around 140,000, and it's still not enough. You can see hyperfine splitting happening in the spectra, but I don't think you can, like, the spectra that you are seeing here in the plot is about 100,000. So it's quite high spectra, quite high resolution spectra, but it's hard to make out such a fine thing. There could be other technique that I don't know about, but yeah, as per me, I don't think so. But there should be. I know that there are some studies which kind of look at the magnetic strengths based on spectroscopy. I'm just not aware about it. What happens when you look at a spectra? Does it make sense? And neutron stars also have spectra. I have never looked at it, so I'm not sure. I'm not really sure how to tell you that. I have never looked at a spectra of a neutron star or even a white dwarf. I only work with main sequence stars and red giant stars. These something like neutron star and white dwarf are a very different kind of systems, where there is a very different mechanisms going on, very different physics going on. So in general, yeah, I think Kshitij has answered that. Okay, Kshitij has answered it. So yeah, we do see X-rays in. Sure, I can. I don't know if I have my LinkedIn. I don't know what I'm called in LinkedIn also, because I rarely. I just look it up. You can connect me through Nakshatra also. Can they connect me through Nakshatra?
Yes, guys, he's also on the most of the groups. I think he's on the
Yes.
WhatsApp community as well. So once again, if you have any questions, do leave it on those platforms. Nagraj, I'll just send you the invite to the Telegram discussions group in case you're not on it. So some
Yeah.
people have questions there.
Yeah.
Okay, great. And I request other people here who may have some background or experience. If you are on the Telegram discussions group, please do address any questions that are put there, if any of you know the answers to them. Okay, it's 9 o'clock, so it's been a very long event, and we had a lot of, I think, questions that got addressed. But once again, you can, if you have other things to address, and especially if they're technical questions, we will definitely make sure that those are addressed as soon as possible. Thank you so much, Nagraj. That was great
Thank you.
and very, very informative. All of you will be able to find the YouTube live recording also. So if you missed any parts of it, or if you want to go back and actually make notes from the event, from the talk, I would really suggest you use the YouTube video as a reference and keep the link with you. We'll definitely post it on all our community channels in about 2 days. Okay, anything else? Yeah, sure. Thank you. Someone asked if we can share the group links. Um, yeah, I will just. So if you can go to, I'm guessing all of you are on the WhatsApp announcements channel, but I'll just post it here anyway. Others, if you're done, and if you have access to our community platforms, you can leave the call. Thank you so much, Nagraj.